Swayam Prabha. Digital India. Educated India.
Hello and welcome back to this lecture series on foundations of fiber physical systems. If you recall, in our last lecture we were trying to deduce an expression for Kalman gain. So, maybe we can start right from that deduction that we were going on, right. So, if you recall, we created a reconstruction error dynamics, and then we were saying that the expected value of the reconstruction error, I mean basically the expectation over the variance. Why? Because this error can be positive or negative. So, we will apply the classical least square minimization technique. So, that would really mean we will try to minimize the variance of that x k tilde term. So, before that what we did is we created a dynamical equation here which represents how this reconstruction error is changing, right. Through the previous slide we have already done that, right. And that derivation tells me that pk is the reconstruction error in the previous one, and then what is the pk plus 1. So, basically this is the variance of the reconstruction error in the kth step and the variance of the reconstruction error in the k plus 1th step. How do they relate? We have figured that out. Now, we are trying to say that we want to figure out what is the value of the Kalman gain such that this variance of the reconstruction error would get minimized. So, as we can see, this dynamical equation tells me that how this variance in the kth step is related to, it can help me to compute the variance in the k plus 1th step. So, in that way I can get a recurrent relation, and that gives me a series of values of pk, and I can see these variances value how that is evolving. Now, I want to tell how that will be minimized. So, for doing that we use a special functional form which is this fxu, okay. And we are saying that this looks like to be in this form, right, and a known result is for this functional form, if such an m exists through which I can relate this qu and qxu terms, right, through this relation, then of course I can represent fxu in this kind of a nice expression, okay. Now, observe something here. In this expression you have a quadratic term, okay. Now, this expression is quadratic in U and the both of the terms are greater than 0. If you see, this term is also quadratic, x transpose then something and x, and this term is also quadratic, right. So, it is kind of that both of the terms are greater than equal to 0, right. So, how can this be minimized? Then the only option that we have is it will be minimum when u is equal to minus mx, right. Now, if under the situation that if we are able to generate this thing in a way that qu and qxu will be related by this kind of a linear coefficient, then we can always now say that since the resulting expression is having all quadratic positive terms, then the only way to reduce it would be to set u equal to minus mx. And if we now apply this well known combinatorial theory result to our update equation on the variance of the reconstruction error. So, we have this update equation which is relating the variance of the reconstruction error in the kth and k plus 1th step. So, I can say that how will the variance be minimized? So, in a similar way I can say that the variance will be minimized in that setting, and that would mean that you replace u with the corresponding Lk term. So, what is really your u and Lk term? Let us see here. So, this was a transpose actually, because this is basically a transpose of the first term. So, this is a transpose. So, that means u is basically nothing but minus Lk transpose, and then right, and what are the other terms here we have to see, right. So, this is what is your u, and what are my other terms from the original expression. Let us just write them down first. So, QXU, this term is this thing, right? QXU is this term. APK, the variance of the reconstruction error in the kth step, QU is this term, and X is your I transpose, that is I only. I mean, yeah, I mean in the transpose manner, of course. So, because it is changing from this to the other format, so of course it should be like this. Now, if we apply these things, these substitutions, right? If you apply these substitutions first into this requirement, that QU times M should be equal to QXU transpose, right? So, if you apply there, you first put the value of QU, so we know what is QXU, right? So, let us take the transpose of that. So, it is this. That would mean this is fine, this is just coming from here, this is just coming from here, and all these values you are just correlating here and you are just substituting here, and then you need an M to exist. So, that is why in this relationship you are now substituting these values, right. So, I am just recapping here. So, your X transpose is I or X is I transpose, or that is same as I, no problem, and U transpose is your minus L k, or U is minus L k transpose. So, just you substitute those values, and this is what you have. Now that means we have to have this inverse to exist, and as long as that does, which is fine, you will have an M. Okay. So, as long as you get the M, you can now simply put that value of M here, and you can get your value of L k. So, let us see. So, L is minus L k transpose, U is minus L k transpose, and minus of, now push your value of M here, and your X is I or I transpose, the same thing. So, this is what you have, right. So, now if you write L k, so you have to take a transpose on both sides. That would simply mean this thing double transpose, and it comes to the forward. So, A P k C transpose plus R 1 2, and on this thing you have to again carry out a transpose. Now, these covariances are all just same. So, that is what you have. Now, of course, the reason we are able to write this is symmetric and also this is symmetric. So, they are same under transpose. I hope we all see that we are taking a transpose on both sides, right. So, this comes to the front and this transpose cancels out and this goes to the back, and again you apply a transpose here, but since these are noise covariances and this C, if you recall, this is also a symmetric matrix. So, and this C pk C transpose. So, this form, this is a quadratic form, not C, but this quadratic form will also be symmetric, and so they remain invariant under the transpose operation. So, that is what we have, right. Now, if you insert so in that way what you get is a expression of the Kalman gain, but observe one thing, this expression is here in terms of the variance of the estimation error in terms of pk, right, but that is not something we really want, right. Eventually we want just the Kalman gain. So, how do I get a value of Kalman gain? So, that means it is related to pk and I have to relate it with the update equation of pk also. So, if I insert this value of Lk into the previous equation of pk plus 1, right, you had this update equation of pk plus 1 and here you had an unknown Lk. So, you push this value to this expression and what you will get, now let me clear this thing and write cleanly, what you will get is something like this. So, first let me write down the Kalman gain. So, Lk and we put this value in the update equation of pk plus 1. So, then the reconstruction error dynamics can be written with this value as something like this. So, this is what you have pk plus 1 update equation you can now express in one line with this term and this. So, as you can see here again you have this quadratic form, right, with A pk C transpose plus R12 and its transpose coming up again here with C pk transpose per R12 transpose, and in between you have this, right. So, the thing is you have two recurrent equations here just like our previous expressions for LQR. What we have here is, well, you know the initial value and the initial mean value, right. So, you can start with P0 as R0 some estimate here, and then you can calculate pk plus 1, right. So, with this you can calculate P1, with this you can calculate L1, right. Now, with P1 you can calculate P2, with this you can calculate L2, and you can proceed in this way, and eventually what you are expected to see is that this L sequence will kind of get to a fixed point, right. When the gains converge, that is what the final Kalman gain value L is what you will get. Okay. So, this is your Kalman filter equation, and this subsidiary equation is going to give you this error dynamics, and what MATLAB does for you is MATLAB solves it in one step by doing this convergence internally. So, let us take an example here. Let us take this example of a trajectory control system. It has got two states, position and deviation from reference. And let us say your control input is acceleration and position is the measurable output of the system. So, not all states are visible, like deviation we are not checking here, and the continuous state space system model is this. It is a well known example you can get in books like Angstrom's book and other books which you have referenced earlier. And if you just create this model in MATLAB, so you can code it up like this. You can define the ABCD matrices, and then you can generate the continuous state space model. You can choose a sampling period. You can create the discrete dynamics now using this C2D conversion with respect to the sampling period. Now, this discrete dynamics you can then assign to each of these ABCD matrices in the discrete time domain, and once that is done, you can create the weight matrices of system state and weight matrices of control input, the Q and R matrices, right, like this. And so, basically for A, you can use A and B itself with this eigen function of MATLAB, right, to choose the size of A, the subset of subsize of A, and create Q and R like this, right. And then you can use the LQR command here to create the corresponding LQR gain for the for this system. So, you are basically generating an LQR controller here, and as a side effect you also get the solution for the Riccati equation, the eigenvalues of these, etc., etc. Okay. So, overall you get this controller designed here. Now, you will need to create this Kalman filter. So, if you see, you can generate an initial estimate of the error covariance. Again, you can have an initial value of p, which you can create using this eigen function of MATLAB again, and you can create this process noise covariance, the R1 and R2, the noise covariance and noise covariance values again, and then you can do a recursive Kalman gain computation, right. So, you can write this MATLAB code. So, essentially you are just creating these matrix transformations like we discussed earlier. So, if you see here, we have taken that R1 to term as 0, right, and you have just defined that R1 and R2 here, right. For that, if you just iterate over this, you will see that the gain value is getting generated, and finally the gain value will converge. Or in other way, you can just directly use this Kalman command of MATLAB, and you can get that Kalman estimator gain estimated directly, okay, and you will see that those values are almost same. So, that is a way to check. So, this is again our picture where we can see that how the closed loop of the trajectory control can be designed along with this estimator in the loop, right. The estimator is basically part of an observer here, and the observer is assumed to know this all the system matrices of A, B and C, and it is incorporating this Kalman gain also here. Okay. So, this is the closed loop with the estimator, and if you just try to plot this system state and the estimate states, right. So, as you can see, x1 and x2 are like this. So, they are almost similar, right. x1 and x1 hat, the estimates of x1 are almost similar, and x2 initially has a deviation. So, if you want to recall what was x2 here, so it is the deviation from the reference, right, and x1 is the position here, right. So, what you can see here is that the deviation will eventually cancel out, and it is able to track the system's trajectory properly. Okay. So, that is about it. With this we end our derivation of how a Kalman filter based estimator can be designed. So, as you can see, it is basically a minimization of a least square setting, and the way we derive the filter gain is using a standard minimization technique of optimization, and with this we will end our lecture. Thanks for your attention.